Chapter 1. Python Concurrency with Asyncio. Let's begin with the core ideas behind concurrency in Python and see where asyncio fits into the picture. 1. I/O-bound versus CPU-bound work. Imagine two types of tasks. An I/O-bound task is one that's mostly waiting around, waiting for a website to respond or for a file to be read from a hard drive. A CPU-bound task is one that's actively thinking hard, like solving a complex math problem. The main thing to remember is that asyncio is a champion at speeding up those I/O-bound waiting tasks. 2. Concurrency versus parallelism. Concurrency is about juggling multiple tasks at once. By quickly switching between tasks, it gives the appearance that they're all happening at the same time. Parallelism is about actually doing multiple tasks at the exact same time. This requires a computer with multiple processor cores. All parallelism is concurrent, but not all concurrency is parallel. 3. The Global Interpreter Lock, GIL. In the most common version of Python, the GIL is a rule that says only one thread gets to run Python code at a time. This prevents true parallelism for CPU-bound tasks in a multi-threaded program. However, when a thread is waiting for I/O, like a network call, it releases the GIL, allowing another thread to run. This is why asyncio, which runs on a single thread, can be so effective. It focuses on managing that I/O waiting time perfectly. 5. The event loop. This is the heart of asyncio. Think of it as a traffic cop for your tasks. When a task has to wait for I/O, it tells the event loop, "I'm waiting now." The event loop then finds another task that's ready to go and lets it run. Once the I/O for the first task is finished, the event loop wakes it up and lets it continue from where it left off. This system of cooperative multitasking allows a single thread to handle thousands of operations efficiently. Chapter 2. Asynchrony Basics. Now, let's look at the basic tools and syntax you'll use to write asynchrony programs. 1. Coroutines, async, await. A coroutine is a special function you can pause and resume. You create one by writing async def instead of just def. Simply calling an async function doesn't run it. You have to use the await keyword from inside another async function. The await keyword is the pause button that hands control back to the event loop. 2. Running your program. To kick off your entire asynchrony program, you'll typically have a main async function and run it with asynchrony.run. This handy function takes care of starting the event loop for you and cleaning up when your main function is done. 3. Tasks, asynchrony.createTask. Using await is great, but it's still a one-at-a-time process. To get real concurrency, you wrap your coroutine in a task with asynchrony.createTask. This tells the event loop, start running this in the background whenever you get a chance. You can create many tasks, and they'll all run concurrently whenever the program hits an await point. 4. Futures and awaitables. A future is a low-level object representing a result that isn't ready yet. Tasks are actually a type of future. In general, anything you can use the await keyword on is called an awaitable. 5. Canceling and timeouts. If a task is taking too long, you can stop it by calling its .cancel method. A much cleaner way to handle time limits is with asynchrony.waitFor myTask timeout 5. If my task doesn't finish within 5 seconds, it's automatically canceled. 6. Common mistakes. 1. Don't run heavy CPU-bound calculations in a standard asynchrony task. Without any awaits, it will hog the event loop and freeze everything. 2. Don't use standard blocking libraries like requests or time.sleep. They will also freeze the event loop. You must use asynchrony native libraries like AI HTTP and asynchrony.sleep that are designed to play nicely with the event loop. Chapter 3. A first asynchronous application. Here, we build a simple network program, an echo server, to see how Asynchronous solves real-world problems. 1. The problem with blocking. If you build a server with standard blocking network code, it can only talk to one client at a time. While it's waiting for a message from one client, it's completely unable to even accept a connection from a new client. 2. The naive non-blocking fix. Switching the network code to be non-blocking solves the waiting problem, but if you just loop continuously checking for new data, your program will use 100% of the CPU, which is very inefficient. 3. The asynchronous solution. Asynchronous provides high-level tools that handle all the low-level complexity for you. You use asynchronous.startServer to create your server. For each client that connects, Asynchronous gives you a stream reader and a stream writer. You can await reader.read to get data from the client and use writer.write to send data back. This approach handles many clients at once because each connection is managed by its own asynchronous task, and the event loop coordinates everything flawlessly. 4. Shutting down gracefully. When you stop your server, example with Control-C, you don't want to cut off clients in the middle of a conversation. Asynchronous lets you catch the shutdown signal and run cleanup code, like waiting for any active tasks to finish their work before the program finally exits. Chapter 4. Concurrent Web Requests. This part focuses on a very common task, making many network requests at once with the AIOHTTP library and exploring different ways to manage them. 1. Async with for resources. Just like a with statement helps manage files, async with is used for asynchronous resources. It's the right way to manage things like a network client session, making sure it's set up and closed correctly. 2. Strategies for running concurrent tasks. There are 3 main ways to run a group of tasks. 1. Asynchrony.gather star tasks. This is your go-to function for most cases. It starts all the tasks, waits for every single one of them to finish, and then gives you a list of the results in the same order you started them. It's predictable and straightforward. 2. Asynchrony.asCompleted tasks. Use this when you want to act on results the moment they're ready instead of waiting for the slowest task to finish. It gives you an iterator that yields each task's result as soon as it's done. The results will come back in whatever order they finish, not the order you started them. 3. Asynchrony.wait tasks. This is the most powerful and flexible option. It gives you 2 sets of tasks, done and pending. It offers fine-grained control, letting you decide to, for instance, cancel all the pending tasks if one of the first ones fails. Chapter 5. Non-blocking database drivers. Here, we take the concurrency patterns from the last chapter and apply them to databases, using the async-pg library for Postgres. 1. Why you need an async driver. Just like with network requests, standard database libraries are blocking and will freeze the event loop. You need a specialized asynchronous driver like async-pg that knows how to work with async I/O. 2. Using a connection pool. Opening a new database connection for every single query is slow. A connection pool is a collection of ready-to-use connections. Your code borrows a connection from the pool to run a query and returns it when it's done. This is much more efficient. 3. Concurrent queries. With a connection pool, you can run many database queries concurrently. The pattern is the same as for web requests. Create a list of your query coroutines and run them all at once using async.gather. Your real-world concurrency will be limited by the number of connections in your pool. 4. Streaming large results with async.for. If a query could return millions of rows, loading them all into memory is a bad idea. Asynchronous databases support streaming results through a cursor. You can then use a special async for loop to process the results one by one, keeping your memory usage low. Chapter 6. Handling CPU-bound work. This section tackles a key challenge: how to handle processor-intensive work with asynchronous. 1. The problem. Asynchronous is single-threaded. If you run a function that does heavy math or data processing, it hogs the processor and freezes the entire asynchronous application because it never gives the event loop a chance to switch to other tasks. 2. The solution, multiprocessing. To get around the GIL and use all your computer's CPU cores, you need multiprocessing. Asynchronous can work with this using a process pool executor. 3. Run in executor. The event loop has a special method, loop.runInExecutor, that can run a normal function in a separate process. It returns an awaitable, which means you can await the result of a CPU-bound function running in a different process, just like any other async operation. 4. The MapReduce example. This is demonstrated with a MapReduce algorithm. 1. Map. A very large data file is split into smaller chunks. These chunks are distributed across multiple processes, which run a map function on them in parallel. 2. Reduce. The results from all the parallel processes are then combined into a single final answer. This parallel approach is dramatically faster than processing the file in a single thread. 5. Sharing data between processes. Normally, processes have their own separate memory. If you need them to share information, like a progress counter, you must use special multiprocessing objects like value or array, and use a lock to prevent them from writing over each other's work, a race condition. Chapter 7. Handling blocking work with threads. This part explains how to use older blocking I/O libraries that don't have an async version within an asyncio program. 1. The problem. You want to use a popular, battle-tested library like requests, but it's blocking and will freeze your asyncio event loop. 2. The solution, multi-threading. Since blocking I/O calls release Python's GIL, you can safely run them in a separate thread without blocking the main asyncio event loop. Asyncio can manage this using a thread pull executor. 3. Run in executor with threads. You can use the same loop.runInExecutor method as before, but this time you give it a thread pull executor. This lets you await a blocking call, and asyncio will manage running it in a background thread for you. While that thread is blocked waiting for I/O, your asyncio event loop is free to run other tasks. 4. Building a responsive GUI. This technique is essential for creating graphical user interfaces. A GUI framework runs its own event loop in the main thread. If a button click triggers a long-running task, the whole UI freezes. The solution is to run the asyncio event loop in a background thread. The button click can then safely hand off the long-running async task to the background loop, which can in turn send progress updates back to the UI thread to keep it responsive. Chapter 8. Streams. Here we learn about a higher-level, easier-to-use API for doing network programming in async I/O. 1. Low-level versus high-level. While you can work with raw sockets using async I/O's low-level Transports and Protocols API, it's often complex. 2. Streams for simplicity. The recommended method is using streams. When you open a network connection with async I/O, you get back two key objects. Stream reader, for reading data from the connection using simple methods like await.readline, and stream writer, for sending data to the connection using methods like .writeData. 3. Non-blocking command line input. A really neat use for streams is to build interactive command line tools. The normal input function blocks your entire program. By attaching a stream reader to the system's standard input, sys.stn, you can await user input. This allows your other async I/O tasks to keep running in the background while your program is waiting for the user to type something. Chapter 9. Web Applications. This section explores how to build fast, modern, asynchronous web applications. 1. ASGI, Asynchronous Server Gateway Interface. This is the modern standard for how an async-capable web server, like Uvicorn, communicates with an async Python web framework. It's the successor to the older, synchronous WSGI standard. 2. Async Web Frameworks. AIO-HTTP, a versatile library that can act as both a web client and a server framework. Starlet, a very lightweight and incredibly fast ASGI framework perfect for building high-performance APIs. Django. The popular Django framework now supports async views. This means you can use await inside your Django code to perform non-blocking operations, like fetching data from a database or another web service, without blocking the server. 3. WebSockets. Unlike the simple request and response cycle of HTTP, WebSockets create a live, two-way communication channel between a user's browser and the server. This is perfect for building real-time features like chat applications or live dashboards, and frameworks like Starlet make them easy to use. 4. Performance advantage. An async web framework running on an ASGI server can typically handle a much higher number of concurrent users and requests per second than a traditional synchronous framework, often using fewer server resources. Chapter 10. Microservices. This part applies asynchronio to the microservice architectural pattern. 1. The backend for frontend BFF pattern. When building an app, especially for mobile, it can be slow for the app to make separate network calls to many different backend services, e.g., one for users, one for products, one for inventory. The BFF pattern solves this by creating a single intermediate API. The mobile app makes one call to the BFF, and the BFF then makes all the necessary calls to the other services concurrently, combines the results, and sends back one clean response. 2. Asynchronio in a BFF. Asynchronio is the perfect tool for building a BFF. It can fire off all the requests to the downstream microservices at the same time using AIO-HTTP and asynchronio.gather. This greatly reduces the overall time the user has to wait. 3. Making your service resilient. 1. Retries. If a network call fails, it might just be a temporary glitch. Building a simple retry mechanism can make your application much more robust. 2. Circuit breaker. If a service you depend on is down or very slow, continuing to bombard it with requests is pointless and slows your own service down. A circuit breaker pattern tracks failures. After a certain number of failures, the circuit opens, and all future calls to that failing service will fail instantly, without even making the network call. This allows your application to respond quickly to users with an error or partial data, instead of getting stuck waiting on a broken service. Chapter 11. Synchronization. This section explains the subtle ways you can still have bugs in asynchronous and the tools for preventing them. 1. The asynchronous race condition. A race condition in asynchronous doesn't happen in the middle of a single line of code. It happens across an await. For example, a task reads a value, awaits a network call, and while it's paused, another task changes that original value. When the first task resumes, it's now working with old, stale information, which can cause bugs. 2. Tools for synchronization. A. Asynchronization lock. This is a simple mutex. It ensures only one task can be in a specific block of code, a critical section, at a time. It's the most basic way to protect shared data from being changed by multiple tasks at once. B. Asynchronization semaphore. This is like a lock that lets a certain number of tasks in at once. For example, a semaphore with a count of 10 will let 10 tasks run concurrently, but the 11th will have to wait until one of the others finishes. It's perfect for limiting how many requests you make to an API with a rate limit. C. Asynchronization event. This is a simple flag that tasks can wait on. One task can await event.wait and it will pause. Later, another task can call event.set, which will instantly wake up all the tasks that were waiting. D. Asynchronization condition. This is the most advanced tool, combining a lock and an event. It lets a task get exclusive access to something with the lock and then wait for a very specific condition to be met before continuing. Chapter 12. Asynchronous queues. This part focuses on a powerful pattern for managing work, the producer-consumer workflow using queues. 1. The producer-consumer pattern. Some tasks, producers, create work and add it to a queue. Other tasks, consumers, pull work from the queue and process it. This is a great way to separate the creation of work from the execution of that work. 2. Using asynchronous.queue. Await queue.put item adds an item to the queue. If the queue is full, it will wait for space. Await queue.get takes an item from the queue. If the queue is empty, it will wait for an item to be added. Await queue.join waits until every item that was put on the queue has been processed by a consumer. 3. Queue use cases. Web applications. When a user submits a request for a long-running job, like processing a large report, the web server can quickly add the job to a queue and tell the user, "We've started your job." Then, background workers can pull from the queue and do the actual work without making the user wait. Web crawlers. A worker can download a page, find all the links on it, and add those new links back to the queue for other workers to download and process. 4. Other queue types. Priority queue lets you assign a priority to each item, so workers will always process the most important items first, even if they were added to the queue later. LIFO queue, a last-in, first-out queue, also called a stack. Workers will always process the most recently added item first. Chapter 13. Managing subprocesses. This section covers how to run external programs from the command line within an asynchrony application. 1. Running an external command. You can use asynchrony.create subprocess X to run a command like ls or gpg. This gives you a process object, and you can await process.wait to see when it's done. 2. Capturing input and output. To communicate with the program, you need to pipe its input and output. This gives you a stream reader to read the program's output and a stream writer to send it input. 3. Avoiding deadlocks. A common problem is deadlocking. If the program you're running produces a lot of output, its output buffer can fill up, causing it to pause. If your asynchrony program is just waiting for the process to exit, await process.wait, without reading its output, both programs will be stuck waiting for each other forever. 4. The process.communicate solution. The safest way to avoid deadlocks is to use await process.communicate. This method handles everything for you. It sends any input you have, safely reads all the output in the background, waits for the program to exit, and then returns all the output to you at the end. Chapter 14. Advanced Asyncio. This final part dives into more specialized topics, mostly for those building libraries or wanting a deeper knowledge of how Asyncio works. 1. Creating flexible APIs. You can use asyncio.isCoRoutine function to check if a function someone gives your library is async or not. This lets you build flexible APIs that can accept and correctly handle both regular functions and coroutines. 2. Context variables. These are like task local variables. They allow you to store data, like a user's ID for a specific request, that is available to a task and any other coroutines it calls without having to pass it as a parameter everywhere. 3. Yielding to the event loop. The command await asyncio.sleep 0 is a special trick. It doesn't actually sleep, it just tells the event loop to pause the current task and give any other ready tasks a chance to run. This can be useful for making sure a task you just created gets a chance to start immediately. 4. Alternative event loops. The asyncio library is just one implementation of an event loop. You can swap it out for a faster one, like UValoop, which is written in C and can significantly improve performance for network-heavy apps. 5. Building your own event loop. The chapter shows how to build a basic event loop from scratch. This reveals that async await is really just a cleaner syntax built on top of Python's generators and the yield keyword. Understanding this provides the deepest possible insight into how asynchronous programming in Python actually functions. That's all for this episode of Geek Capsule. We hope it gave you a fresh perspective on the world of technology. We'd love to hear your thoughts, so feel free to leave a comment or share your feedback. If you enjoyed the show, don't forget to subscribe and join us next time for another essential read. Until then, keep your curiosity sparked and your mind open.